right now. Okay. You can see my PowerPoint presentation now on the screen?
Not yet.
No.
Okay. To be honest, I don't understand when it is maintained and when it disappears. Maybe if I... Okay. Now it should be on the screen.
Yes.
Okay.
Yes.
Okay, so let's start the topic of today, which is particular techniques of social network analysis, the particular case community detection. First of all, a brief introduction to graph mining. As the name says, it's applying data mining to graphs, for example, to social networks. After a first overview, we step into community detection, and those are the tools you will need for your work. Okay, so there is a paper by Nettleton which provides this overview, where we can see how to. He introduces first some background. Those numbers are the chapters of his paper. I uploaded the paper, but we will focus on the particular topic of communities, which you can see down here, which are the chapters 2.4.9 and 2.4.10. So this is just a brief overview of all the other topics which are still not relevant today. Okay, so he introduces the concept of graph mining, which means data mining on graphs. And within graph mining, there are topics like prediction, applying supervised learning, pattern detection, okay, metrics, all kinds of metrics we will need in order to evaluate predictive models. Here we speak about data processing. Yesterday we mentioned already the notion of streams, data streams, as we have incoming data. And finally, communities. And the focus of today is here on communities, community detection. Perfect. Here we have an example of a citation network. I mentioned that yesterday. For people from academia, we like citation networks because it's important for us. Anybody outside academia doesn't understand what it is, so we are living in a strange world where papers are important. And anyway, so what we can see here is different disciplinary areas like physics, mathematics, molecular biology, medicine. So we can see several elements. For example, each node is an area. The size of a node is proportional to the number of papers published in that area. We have links, mutual dyads among areas. For example, here we have, well, each link refers to citations. For example, papers from medicine cite papers from molecular biology, and vice versa. The size of the links is proportional to the number of citations among those two areas. And of course, as we can see down here in this legend, we have different flows from one area to another, can be different to the opposite direction. Where is it more obvious? Yeah, for example, this one here, medicine, molecular biology, it's not the same amount in both directions. Okay, so that's an idea of a social network, and we get a first notion of a community. There is a community of what we call life science over here. So there is a high density of citations among those areas, and they don't have that much relation with areas over here. But there's another community where we have physics, mathematics, chemistry, basic sciences. with high density of citations among those areas. And that's a first idea of what a community could be, the notion of density, which we are going to introduce formally in a couple of minutes. Okay. Question is how to establish links. We saw that already yesterday. Those four sources of information to establish a link. We also would like to know the importance of a link. So we have to define what a component means. For example, we have a strong component, like for example in this case, which we will also use for communities, if from each node of the component there exists a path of directed links towards each other node. That's the case here. From each node, a directed path to each other node. That's not the case in a weak component. For example, from D to F, there is no directed link or directed path. For example, we can go from D to E, but not from E to F. We can go from D to G, but not from G to F. So from D to F, we have a path, but it's not a path of directed links. Okay, that's what we call a weak component. That means, for example, there are no, if we use the terminology of Facebook, for example, if a link would mean being friend, there is no friendship relation from D to F, for example. Whereas from A to C, in the strong component, we have the relation A is friend of B and B is friend of C. So there is a path of directed links from A to C via B, well, also indirectly from A to C. So strong component here, weak component, and isolated components, just a node without any link. Having that in mind, we can now define a community. Question to you: what do you think? How can we define a community, formally speaking? Any notions? Okay, let me look to the chat. Clusters, very good. That's a very important concept. Clusters, which we did not introduce yet, but we will introduce it later today, I think in the afternoon session. Okay, clusters. Clusters of which element? Vinodip, what do you think? We are clustering which element of a social network?
Clustering the similar sorted items, similar nodes.
The nodes. So we are using clustering of nodes in order to determine communities. Very good idea. That's what we are going to see today in the afternoon session. Clustering of nodes. But that's not the only way to determine communities.
Cluster of strong components.
Okay, so we will look into components where we have as an important notion links. So we will have to look into links. That means we're counting links among a component. Yeah, keep that in mind, counting links. So let's start. We define, formally speaking, a graph G. A graph G is a tuple of two elements, a set of vertices V and a set of edges E. We had that already yesterday. That's the typical definition of graph theory. The graph is described by those two sets, the set of vertices or nodes and the set of edges or links. Okay, and a subgraph is simply a graph by itself where V prime is a subset of the original set. So the nodes are a subset of the original set of nodes, and the edges are a subset of the original set of edges. Okay. In sociology, okay, that's the definition in mathematics. In sociology, we have components, as some of you said before, it's a subgroup of individuals whereby all the individuals are connected. So here we have the connectedness. That's an important notion in sociology. Okay, we need a component with connected nodes, connected individuals, in order to establish a community. There is a algorithmic definition, and that's the one we will use mainly here: density and also connectedness, but we will focus on density. And also we can define community based on a particular application, for example, similarity of nodes or edges, which I use interchangeably. That was the notion Vinodeep said, similar behavior of nodes. So we can cluster nodes in order to have similar nodes together in one community. Okay, so here we define density. Yesterday, someone, I think it was Moritz, mentioned the number of formulas. I want you to look beyond the particular formula and to see what's going on in the formula. So for example, we define the intra-cluster density like this. That's what we have here. But again, don't look into the numbers n times nc minus 1. That's too detailed. Let's have a more general view of this formula. What do we have here? We have a graph. We start with a graph, number of nodes and links. Okay, and we have a subgraph. And for this subgraph C, we define this notion. Okay, and we have a quotient in the nominator. We have the number of internal links of C. And in the denominator, we have this number. And I would like to switch to a whiteboard, which will take just a second, in order to explain this concept. Okay. Okay, so here we go. Let me share the screen. Okay, you can see now my whiteboard, which says Tuesday, September 15.
Yes, we can see.
Okay. So each dot I'm showing now here represents a node. Black color, we have the nodes. With red color, I'm showing the links. And with a different color, I just mention this community. That's my community C, okay? Whereas all this, that's my social network. That's the graph G, Okay, so G is the entire graph with all nodes and all edges. C is a subgraph with just the nodes inside this circle. This one should be inside as well. And the links inside the community. Okay, so now we are going to define the density of this community. And the formula says it's in the nominator, we have the number of links. So we are counting the number of links. 1, 2, 3, 4, 5, 6. So it's 6. That's the nominator. Okay, density is equal to 6 because we are counting 1, 2, 3, 4, 5, 6 links inside the community. And let me go back quickly to the presentation. So we have the number of internal links of the community C. It was 6 in our case. What do we have in the denominator? NC, that's the number. Who knows this expression? What does it mean in plain English?
Transpose.
Say it again, please.
Transpose.
V prime is the set of nodes in our community. And cardinality of V prime, that's the number of nodes we have in our community. Okay, and C, the number of nodes in community C. And this formula we have in the denominator. Again, don't get afraid of formulas. That means the number of possible nodes we have in our community. So if we have NC nodes, this formula gives us the number of possible links inside the community, the number of possible links. If all nodes would be connected one to each other. Okay, so the number of possible links. With that in mind, let's go back to our whiteboard. So we have NC is 1, 2, 3, 4, 5, 6. This one should be inside as well. Okay, sorry for that. Again, 1, 2, 3, 4, 5, 6 nodes. So NC is also 6, the number of nodes inside the community. And the denominator is now NC times NC minus 1 divided by 2. So it is 6 times 5 divided by 2. That's the denominator. And that is equal to 15. So in the denominator, we have the number 15. But how can we interpret this number 15? That's the number of possible links that could exist in this community. If each node would be connected to each other node, then we would have 15 links. Yeah, we don't have, for example, this connection, and we don't have this other connection. So we don't have all connections within this community. If we had all connections, all links, then there would be 15. Okay, so the general formula to determine the number of possible links is number of nodes, 6, times number of nodes minus 1, 5, divided by 2. 6 times 5 means each node with all other nodes. So we have 6 possible nodes, each one of those with 5 other nodes, divided by 2, because we don't want to count twice the back and forth. Okay, so that's the generic formula to calculate the number of possible links if we have, in this case, 6 nodes. Okay, so the density, according to our definition, is 6 divided by 15. Any doubts so far? Yeah, we observe an entire social network, this graph G, with all the nodes here and all the edges, all the links, okay? And we say, just a second, Mari, we say if this set here would be a community, we still don't know if it is a community, if this set here would be a community, what would be its density? And the formula tells us how to calculate the density. The result is down here. We take the number of links we observe. We can look at this and we can count the number of links. 1, 2, 3, 4, 5, 6 links. That's the nominator. The denominator, we have the number of possible links. And that's quite intuitive. You get my point now. It's beyond the formula. Don't get afraid of formulas. The formula is quite intuitive. It says the number of links I observe divided by what I could expect as total number of links. Okay, I observe 6 links, and at most there could be 15. And this is the formula to come up with the number 15. Number of nodes times number of nodes minus 1 divided by 2. So that gives us an idea of how dense is this community. How many links do I have related to how many links could I have at most? Yeah, Mari, please.
Yeah, I just had a clarification. Is it indifferent for directed and undirected links, or does it matter at all, this calculation?
You can define density for both cases. In this case, I'm on the, let's say, simple side. We're just with undirected. You can, of course, extend the definition to directed graphs. And then you have to see how you count a mutual link. In that case, you should count it twice if it is directed.
Yeah, that makes sense.
Let's stay simple for the moment. In undirected graph, a link is counted once, and that's why we have in the denominator of this formula divided by 2, because in undirected graphs you don't count it twice. Okay, but yeah, a very good question. So let's go back to the presentation. So this notion, this formula, gives us an idea of the density of a community C. Yeah, the number of links I observe inside C divided by the number of links we could have at most within C. Okay, any doubts regarding this formula? Again, the concept is very general. I won't go into detail every time we have a formula, but I wanted to set up the idea of this formula. What we observe divided by what we could get at most. Okay, and the next formula is very similar. So we analyzed it in more detail for the intra-cluster density within C. Now we can define the intercluster density. That's the number of intercluster links. Those are links that leave our community divided by the number of possible links we could have at most leaving from C. Okay, let's go back to the whiteboard. So how many links do we have leaving community C? One, just this one here. Okay, so that's this formula. Just leave it like that. That's the intra. Intra means within, inter means between. Okay, intra density, the one we saw already. Now I will put here the yeah, let's put it intra. The intradensity is equal to, it's again a formula where we have a denominator and a nominator. In the nominator, we have all the links we could observe that are leaving from C. Just one. How many links could we have at most leaving from C? And there again, we have this let's say, kind of ugly denominator, but now we're not afraid anymore. We are just looking how many links could we have between C and the rest of our network. So we take each one here and we count how many links could we have with this, with the rest of the network. I'm not going to do the calculation because there are many, and that's so I just put an x here. Understanding x is the number of all possible links we could have leaving from C. The precise formula is the one we see here. Okay, number of intercluster links of C, all those that leave C, divided by all links that could go from NC to the rest of the network. The number is like this one here. But now we are not afraid anymore. It's the number of links inside C times the number of candidates. So that's the number of links of the entire network minus those that are inside. So from inside C to outside C, that's the potential number we have divided by 2. Again, divided by 2 because it's an undirected graph. Okay, so we have two notions of density. Intracluster density means density within the community. Intercluster density means the density of links that leave our community. Question so far? Okay. So having said that, having defined those two densities, now we know how to define community for a subgraph C to be a community. What do we expect? We expect to have the intracluster density high and the intracluster density high and the intercluster density low. That's what we express here. So we expect the intracluster density larger than the average link density, which means those outside. Yeah, at the same time, the intercluster density should be smaller than delta G. Okay, so the first one should be a large number and the second one a small number. In that case, C is considered to be a community. Let me go back to the whiteboard. Okay, so if the density inside the community is large and the density of those that leave our community is small, then the community is what we call here a community, then it is considered to be a community. We started by just fixing this as a community. In order to get this name, community, the density inside should be high, the density outside should be low. That's it in simple terms. Okay. Any doubts so far? Yeah, Christian Meyer.
Doesn't that imply that we need a starting iteration in order to start evaluating this?
Yeah, very good question, Christian. So far, I didn't tell you how to determine C. So for the moment, I'm fixing C. I'm saying, okay, let C be a subgraph. So this is not an algorithm. Christian, your question implies to have an algorithm. So we need something to start with, and then we will determine our community. Here, what I did so far is I assume a set as given. I assume C as given. And then for this subgraph, I define both notions. I still didn't tell you how to determine C. And that's going to be the next step. That's going to be our algorithm. And then we will need a starting point. Do you get the difference? So one thing is to define the two densities. And here we just define the two notions of density for a given set C. a given subgraph C, I define both concepts. I didn't tell you how to determine C. How to determine C is the algorithm, and then, as Christian said, we will need a starting point and some steps on for updating. Did you get the difference, Christian?
Yeah, I understand. In real life, it's not that easy that you always have C. You might have to come up with a known value for C or calculate C, basically, in order to fulfill all these steps that we just learned within this slide.
Exactly. So as a first step, I define the two densities for a given set, for a given subgraph. So for any subgraph, I can define those two densities. And next, I will tell you how to determine a subgraph that is considered to be a density, to be a community. Okay? Based on these definitions. Okay. So I guess you can see now the PowerPoint presentation, two densities, inside a subgraph and outside a subgraph. There are different definitions. This one, I just mentioned it. We will use density to determine communities. Where is it relevant? So there are different applications. Maybe, yeah, let's do it like this. Maybe each one of you can start. Each one of you can give me some examples. Where do we need community detection? There are some application areas as a starting point: customer segmentation, recommender systems, storage of graph. Maybe that's too much computer science, policing, gang detection, health, and there could be others. So maybe we can have a couple of applications from this list or whatever you want. Maybe, let's say, you can mention 2 or 3 applications. Maybe some of you who wants to start. Gaurang raised his hand, please. Gaurang?
What about genetic studies?
Same.
Like genome mapping.
Yeah. Why don't you start? So again, I would like 2 or 3 or 4 of you to mention, to develop some applications of social network analysis where you can use the concept of community detection. I have here some candidate applications. Gaurang mentioned another one, genetics. Okay, so, and I would like you to develop the idea how to use community detection in the area you pick. Gaurang, could you start, please? So in genetics or genomics, how do you think you build a community? So you have to tell me first, you have to tell us, what's your social network? What are nodes? What are links? And links is the critical part, the tricky part. How do you establish a link? Once you define the network, then I would like you to tell us what is a community good for? Why do you want to do community detection? We still don't have the tools to do community detection, but maybe you can tell us how community detection would be useful in the particular application you picked, which is genomics. Okay, could you please start?
Right. So basically, usually nodes would be individual people, but I think instead of going to individual people, we could have nodes as these hospitals who do these kind of genomic studies, or even research centers. And then there will be links, obviously, between based on the genome of the people who are actually in that study group. The community will be based on, for example, a particular set of people who have a certain genome. They are more prone to diabetes, let's say, or heart attacks, or I'm not sure if that's a genetic disorder, but the diseases basically which are related to genetic disorders, or that's how they are given or inherited from one generation to other. And that would and that would help in turn develop, based on this data, I would say preemptive medicine.
Okay, yeah, very good. Well, we are all not experts in the area, so it's okay. We are free to invent some applications since we are not experts. Yeah, I see there are a couple of you raised your hand. Just a second to understand the application Gaurang mentioned. We have a social network, a graph with vertices and edges. Vertices are, as far as I understood, hospitals where they run some studies. Edges among hospitals are introduced if they collaborate in the same study. That was correct, Gaurang?
Yes, basically, there's a lot of, just to give an example, John Hopkins Institute, which also is a hospital in itself, they do a lot of these research studies with their patients. So
I
to
understand, but
generate
again, to define precisely, what are the nodes, patients or hospitals?
the hospitals actually, because then
Okay.
we already have a lot of data sets.
Okay, so the nodes or hospital edges among hospitals are built if they participate in the same study. That's the way we can build our social network. And
Right.
suppose,
The social network essentially is much wider because then we have data from different hospitals all over the world.
exactly, and that's what's happening right now. Different hospitals and research institutes are collaborating to get the vaccine for coronavirus. Okay,
Right.
so a community within this kind of network could be interesting to understand who is and or who should be working together. Okay, interesting. So again, we don't have to go into detail since we are not experts. I can see there are 5 comments. I understand Zoom gives me the sequence, and the sequence I can see it here on the screen. That's the sequence. You raised your hand. First one was Christoph Speitkamp, please.
Yes, I would say another application is maybe the field of e-commerce online shops, for example, Amazon. The nodes would be, for example, products, and there's a link between products and nodes. If one customer is buying 2
Very
or more
good.
products in one process.
Very good.
So you can build up communities to see which products are bought together by the same customer.
Exactly. Very good. On the screen, we can see now relevance of community detection. Actually, you mentioned the second bullet point here, recommender systems. That's what Amazon does. That's what Netflix, Spotify does when they are suggesting something, recommending something based on products that go together. Yeah, very good. The case of, I can see here, Yi is Xiao. I guess Xiao is your first name. Yi,
That's my last name. Yeah,
Xiao
so
is your last name. Okay,
Xiao
sorry.
is my last name.
I have a Japanese friend where Xiao is his first name. So your first name is Yi?
Yeah, my first name is Yi.
Yeah,
Exactly.
perfect. Yi, please go ahead.
Yeah, sure. In an application in organic chemistry should work. Taking nodes, taking chemicals as nodes, and taking links as reactions. So if the chemical can be reacted and become the other chemical in 1 or 2 steps of reaction, then we can establish a link. Then
Great.
by doing that, we can establish a network, knowing that from which chemical we can easily become the other chemical, and then thus build a neighborhood, a community that showing that the how they are formed and the similarity of each of the chemical groups.
Yeah, interesting. So we establish a network of chemicals.
Yeah.
Nodes are chemicals. Links are reactions that could be interesting. Again, we are not experts, or maybe you are, I'm not. And in that case, a community would be chemicals that show the same reaction.
Yes.
Yeah, great.
Thank you.
Yeah, thank you. Christian Burmeister.
Yeah, I think what I wanted to say is very close to what Christoph said. So as I said, I'm just working on my startup, and I want to find out the communities of artists, because for jazz fans, for instance, or for any music fans, yeah, people fall in love with an artist with a certain style, with a certain style of music, in a certain style of playing, which is very important in jazz. And I want to build up a catalog of videos, of products people could buy. And for me, it's very important to understand who are the artists who are related with each other. Of course, you could go through the albums bit by bit, but you could also have a map or some sort of automated system to find out where the clusters of communities that you need to have in your catalog. And obviously I can't start with everything. So I need to start with one cluster or one community and then build it up from there gradually. So it's really a thing of, multiple buying, not a suggestion engine, more like a completion of catalog, what I need to have to satisfy these customers.
Yeah, very good. Interesting. Also, in the sense of recommender systems in your particular area. When did you start with your startup, or what's your current phase now?
Yeah, well, I'm still building the MVP. So I started, but basically the idea came in place late last year when I did a workshop with Simon Phillips. Maybe some of you know this guy, it's a drummer. And I was like, oh, actually there's no channel for high quality concert videos. Spotify and everything, they do like mass volume music, but jazz musicians are in the long tail and they don't earn money anymore. And there's no channel to distribute this music to the very specific target group who are willing to pay for very high quality music a higher price. But these people do exist. I know them. I meet them at these concerts. And so we were like, okay, we need to find some sort of mechanism to distribute this music to these people. And I'm in the phase of building the catalog. So to collect videos from the labels and from the artists, but also building up the group of followers and the group of customers who I want to distribute it to, and use social media marketing to reach out to them as efficiently as possible. So I need to really know who are the people, who are the communities, who are the channels to do that.
Okay,
I
great.
want to launch in October or November when the second wave of Corona comes in.
Yeah, okay, great. Good luck. And hopefully the topics we are seeing during this course help you to define communities of customers.
Oh, it's highly relevant. That's
Okay.
exactly what I'm doing. Yeah?
Yeah, great. Next, I see on the list Piyush Kulkarni, please.
Yeah, sure. So the idea that I have in mind is for developing or designing healthcare services so governments can act more efficiently. So in my case, the nodes would be the hospitals, and the links here, there could be multiple links, and multiple links are the various sets of data points from the patients. So let's say if patients are infected with dengue from one particular community, then the hospital will have a data on in which year the cases tend to rise, and then acting on this, the government can plan de-infecting of the communities, or spreading awareness, so that the government can basically protect the communities from the widespread of the disease or epidemics that we have. So this is what I had in my mind.
Yeah, great. First, it's always important to define very well the social network. I understood that nodes are hospitals. I didn't quite well understand, how do you establish links among hospitals?
The data points, once you have a patient registered in the hospital, you will have various sets of data points on each patient. So let's say the area that he is, the date or the time period which was he detected in, and then these could and since you will have patients going to different hospitals, the hospitals could share the data, and then they can use to build. They can probably also develop an algorithm based on this, and then which they can later on submit to the government or the healthcare provider of the services.
Okay, very good, thank you. And finally, I can see here Alexander Gladys, or is it your classmate? I understand that there are two of you. By the way, I need also the list of attendance. Let's do that later. Okay, so Alexander, please.
Going back to our example of risk and fraud detection in online banking from yesterday, I think if you take individual bank accounts as nodes and transactions between bank accounts as links, then you can establish certain communities of bank accounts that interact with each other on a regular basis. So if there are any transactions outside of these communities, then that might be a red flag that something fishy is going on.
Okay, great, good idea. Thank you. As I can see on the chat, you're already telling me if you're present. Please go ahead. Same idea as yesterday. That's only because I don't know how to use the Moodle system. Maybe there is a more convenient way to do that on Moodle. So for today, please go ahead like this. And maybe someone can tell me how to do it in a more efficient way on Moodle. If not, this works. This is fine. So please tell me if you're present right now. Yeah, okay, that seems to work quite well. Thank you.
I don't know how you need to summarize this information, but in the previous course we had a poll. So like I don't know which website the professor used, but he basically just sent us a link and we had to fill out our name in a different poll
Thank
kind
you.
of
Thank you,
system.
Mari.
But I think it also works in the same way.
Yeah, sure. I will do that. The organizer sent me the list of attendance for each. It's a matrix for each day, for each student. I can share that as a Google Doc, and then you just tell me if you're present or not. Yeah, we can do that. Thank you. Okay, great. So community detection is relevant. You mentioned several applications. Some other applications are shown here. We have been working with our police department in detecting gangs. That's a current research project. We're going to start, well, we have been working so far, but we will start in October a new research project where we do community detection on social networks of suspects. And there we want to understand how crime works. Health, another area where I could show the application we see now on the screen. Again, do you see the screen with the healer system, which says community detection in social networks? Yes or no?
Yes.
Okay,
yes.
Thank you. So I just want to mention the system. On the link down here, there's more information. There's also a video, quite nice. Just mentioning one application people did in Los Angeles. They had the problem of homeless people. Okay, so homeless people living on the street, that's a problem by itself. But additionally, some of them were positive on AIDS. Okay, so nowadays it would be also the virus, coronavirus. Okay, but at that time, the problem was those homeless people that were positive on AIDS. The mayor of Los Angeles didn't have enough resources in order to prevent the spread among all of the homeless people. So he or she didn't have enough resources. So what was the solution of community detection in this case? Try to think you as mayor, or maybe even better, you as a consultant to the mayor of Los Angeles. The mayor tells you, you know what, there are many homeless people. I don't have enough resources in order to prevent the spread among all of them. So tell me, what can I do? And you took a class on social network analysis. So what would your suggestion be? Look at this figure here, which says heal at the center. That's a social network. Of course, it's not a real social network. That's a social network, a symbolized social network of that application, where each node represents a group of those homeless people.
We can think maybe the homeless people as nodes and the links as the interactions between them, and we can cluster them according to their positivity in AIDS.
Say it again, please. I didn't hear it quite well. Could you say it again, please?
Okay, so maybe we can think nodes as homeless people and the links as the their interactions between each other, and we can cluster them according to their positivity in AIDS.
Yeah, exactly. Very good. So here is where they applied community detection. They got information regarding the interaction of those homeless people. I don't know exactly which kind of interaction, but that's what they got, interaction. And by the way, that's always the problem. How do you establish a social network? How do you define the links? Based on which information? Based on which data? Because it's always not easy, but you could always think of some way how to establish links. But then the next step would be to get the data in order to establish the links. So they established a social network of all homeless people in that area. Then they did community detection, and they told the mayor, actually the consulting project was done by colleagues from the University of Southern California. It was a project they offered to the mayor of Los Angeles at that time. And they did community detection, and they told the mayor, okay, since you cannot act on each one of the homeless people, which would be, let's say, ideal, but there's not enough resources, so focus on the leaders within each community. So leader is the most important node within a community. And to do so, you first have to do community detection, because they are not evenly distributed. There are, within that group of homeless people, there are communities where it's high density. Okay, so again, there's a notion of density, high density of interaction within one community, but low density of interaction among communities. And that's exactly what we introduced here. Okay, so high density within a community, but low density among communities. Okay, so that's what they applied here. They identified communities with high interaction within that community, low interaction among communities, and for each community they identified, they pinpointed the most important nodes that, well, that had most interactions. And if you have limited resources, I recommend you to focus on those most important nodes, because that's where your investment has highest impact. Investment in, let's say, time or in resources. In the particular case, it was using, I think, I'm not sure, I think it was using a vaccine against AIDS, for example. But of course, you could think of any kind of measure where you want to concentrate on few people. Since you don't have enough resources, the question is on whom to concentrate. And the answer was the most important nodes within each one of the communities. Okay, to do so, we need community detection, and that's what we are doing next. It's now 7:10. The morning session from now on is just 2 hours, 11 to 1 p.m. So we have 1 more hour before lunch, and the afternoon session is 4 hours, 2 to 6 p.m. Okay, so before lunch we're going to introduce, I think, one of those community detection techniques. The paper by Papadopoulos and colleagues from 2012 is on the Moodle system. We will focus on those 3 areas: vertex clustering, quality optimization, and divisive community detection. So for each one of those 3 areas, we will see one candidate, one technique, together with R code. So what you mentioned yesterday, today I'm going to share R code, at least for quality optimization and for divisive cluster, divisive community detection. So from then on, you do have the, well, let's say, one R code in order to do community detection. I'm going to skip vertex clustering. Okay, the first area, vertex clustering, that requires, let's say, traditional clustering. I will skip that, and we will jump into quality optimization. And I guess you can see the cursor moving here on the screen. So there is modularity maximization. We're going to introduce this concept, modularity maximization. First, that's quality optimization, and then divisive clustering. We will do edge removal. So that's one topic. We will see actually the second tool we're going to introduce today, edge removal. The first one is modularity maximization. But let's go step by step. We skip vertex clustering and we step into quality optimization. So the basic idea of quality optimization, and now we're coming back to the question Christian Meyer raised when he said, well, what's the starting point? How do we iterate? So now we know how to define density. We introduced the notion of density. Now we are going to introduce a technique, an algorithm that is based on density or something something similar to density, but now we're going to introduce an algorithm. We could use density, the concept we introduced already, okay, but we're going to use something very similar, but it's different. It's not the exact definition of density, but the notion is very similar, and it's called modularity. Okay, and literally speaking, we have this, let's say, it's not a formula, but literally speaking, it's the notion we have here. We are counting the edges inside the community minus the expected number of edges inside the community for a random graph. What does that mean? And to introduce or to explain this idea, I'm going back to the whiteboard we had before. So that's the whiteboard we had before in order to introduce the definition of density, intra and interdensity. The same example helps me now to introduce modularity. So modularity, as we saw it before, is the number of edges inside a community, which still is 6 for this community, minus, and then there was something strange, minus the number of expected edges. In density, we start with the number of edges and we relate it to the number of possible edges. Yeah, that was 6 divided by 15. You remember? That was density. Now we say, okay, modularity is the number of edges we have here, 6, minus, and then there was a kind of strange definition, minus the expected number of edges inside that community for a random graph with the same node degree distribution as the given network. What does that mean? Okay, let's have a look at the whiteboard. So here we have a social network. For each node, we know its degree. What is the degree of a node? You remember? A degree of a node.
The links.
Number of links.
Miri, very, very good. The number of links. So for example, this node here has degree 1. This node here has degree 2. So the degree of one node is the number of links of that node. And now the notion of modularity says, I'm observing this social network. In this social network, for each node, I have the degree, its degree, the number of links it has. So if I take all those degrees, there is a distribution. Okay, there is a distribution that tells me what's the number, or how is the number of links distributed. And as an idea, we think there is a high density here, but a low density among communities. So we expect the degree for those nodes to be higher than if it had a similar distribution all over the social network. And that is what we relate. So we relate the number of links we observe, and we assume it's higher than it would be if all nodes had the same degree. That's it. So we relate the number of links we observe here with the number of expected links we would have in this community if the number of degrees would be the same all over the network. Okay, and that looks like this. Here we are. Okay. Just a second. Yeah. You can see the screen quality optimization. Yes or no?
Yes.
Yes.
Yeah, thank you. So we have the edges inside the community. That's the easy part. We just count what we observe minus the expected number of edges within the community, same community, but if the node degree would be the same all over the network. Okay, and we don't do the calculation right now. We will see a formula, but again, I'm not interested in the formula. I'm interested in you understanding what the formula says. And this notion, the observed number of something minus the expected number of something, that's known in statistics. There is a test in statistics that does something similar. If you don't know it, I don't expect you to guess it. But if maybe you know the test, the particular test that says something about the number of observed edges minus the number of expected edges. You know that test? Yeah, okay, it doesn't matter. If you don't know it, you don't guess it. It's the chi-square test. In statistics, we know the chi-square test that says something about the number of observed items minus the number of expected items. And this idea is now applied here in the concept of modularity. Number of observed edges, that's what I can see in the community, minus this strange definition, which now is not that strange anymore. It's what we would expect if the distribution would be homogeneous. Okay, and that was the contribution of Closet, Newman, Moore. You remember that was the algorithm we saw yesterday. Now we're going to work with this algorithm. We have here the paper, and that's the formula. Again, I don't expect you to go into the formula. I'm just saying there is a formula that measures exactly the notion of what we have here. So we want to somehow, again, we want to detect something like density. It's not density, now it's modularity. Number of edges we observe minus expected number of edges we would have in the case of a homogeneous distribution. Okay? And here you have the derivation of this formula. Okay, that's how we derive the formula. The edges inside a community, we just count. We have here A, I, J, the adjacency matrix. Okay, so A, I, J, I'm just mentioning the elements. A is the adjacency matrix, which tells us if node I and node J are adjacent. But now we don't have just 1 or a 0, 1 in the case of having a link, 0 in the opposite case. Now we can have a weight of the edge between node I and node J. Again, I'm not interested in the formula. I'm just telling you that we can use a adjacency matrix where each link has weights. For example, according to the frequency of phone calls. Yeah, now we have a weighted adjacency matrix. And having the weighted adjacency matrix, we can count the number of links inside a community, and we can determine the expected number of links inside that community given the hypothesis of homogeneous distribution. The difference, that's exactly modularity. Okay, so that's the formula. I want to show you one application of modularity, and then we will go into the R code, and we have a bit more than half an hour. There is a method called the Louvain method, according to the city in Belgium, presented by Blondel and his colleagues in 2008. They were working at the University of Louvain at that time, and they developed this method, Louvain method, that works using modularity. I want to skip the next 3 slides, show the application first, and then we come back and introduce the method. Okay, so I want to start with the application. Blondel, they applied the Louvain method, which is based on modularity, to a telephone network in Belgium, to a Belgian mobile phone network. They had 2 million customers, okay? And as you know, in Belgium, they speak mainly 2 languages, French and Dutch. Of course, they speak other languages as well, but mainly those 2 languages. They built this network in the following way: nodes are customers. The size of a node is proportional to the number of customers, and the network shows only nodes with at least 100 customers. Only communities composed of more than 100 customers have been plotted. So the very tiny node here represents 100 customers, and the size of nodes is proportional to customers. A link between 2 customers, between 2 communities, is established if there are phone calls among those communities. Green indicates the Dutch-speaking community. Red indicates the French-speaking community. And there are some few nodes in between. So if we do a zoom, for example, on this node here, we have a mixture of French and Dutch-speaking customers. That would be Brussels, some cities where both languages are mixed. So here you can see quite clearly that there are 2 large communities, clearly separated. The Dutch-speaking people, they call each other, and the French-speaking people, they call each other. Of course, I know I'm simplifying a bit. I know it's not like that, but I think that's what they are showing with the application. Okay. Yeah, that's one of the applications of modularity. And yeah, we will see our code, but before we are doing so, I would like to mention how the method works. It works with 2 phases, and that's what they call one pass. In phase 1, they use modularity, the concept of modularity, in order to build communities. So they say for each node, if the node goes by itself or if it is merged with another node. So they say if node I should be removed from its community and placed in the community of J. How? I'm not concerned about that. So they say in phase 1 how each node should be merged with other nodes. And they repeat that part until no gain and modularity can be realized. Okay, so that's phase 1. And in phase 2, they consider each community as a new node and re-establish links among those communities. And all this is stopped if modularity cannot be improved. Here is a simple example how the 2 steps work. We start with a social network. So here we have nodes, for example, telco customers, and links, maybe phone calls among telco customers. There is no community, all nodes have the same color. In the first step, okay, we do modularity optimization. That was phase 1. So each node is put together with another node in order to maximize modularity. And that provides, in the first pass, this network. We have the same network as before, but now we identify communities indicated by color. So there is the red community, the green community, the blue and the light blue community. In the second step, we just collapse all nodes from one community into one node. So the green node now represents all nodes from the green community, and the same for all other colors. The red node represents the community for all nodes from the red community. Okay, so we kind of shrink the original network by first identifying communities and then representing each community by one node. And that's what we apply iteratively. First phase, modularity optimization. Second phase, community aggregation. And that's what they call one pass. And those two steps are repeated iteratively until a stopping criterion is fulfilled. Okay, so going back to the initial idea, we introduce the notion of modularity, which says somehow we want to count we count the number of edges inside a community minus the expected number of edges. There is a formula which is not important anymore. There's a formula that measures modularity. The important thing for me is to understand, what does it mean? How can we interpret modularity? Number of edges we observe minus expected number of edges we would have in the case of a homogeneous distribution. Based on that concept of modularity, Closet, Newman, Moore developed the algorithm. Okay, here's the formula. The algorithm that has two phases. In phase one, we detect communities by maximizing the concept we just introduced. And phase two, they collapse all nodes from one community into one node. And this is repeated until modularity cannot be improved anymore. A simple example has been shown here, and a real life example was the one with the telco network in Belgium. Questions so far? Okay, Simahat, please.
Yes, well, I didn't quite understand the applications of modularity for the communities. How is it different from the clustering?
How is it different from? Say it again, please.
How is it different from the clustering?
From clustering? Okay.
Yeah.
Yeah, we have to go back to this slide. There are 5 different areas for community detection, and maybe there are more, but Papadopoulos identified those 5 areas. In our course, we're going to speak about 3 of those 5 areas. Vertex clustering, which we didn't see yet, but that's the answer to your question, Simahat. We just introduced one technique where a quality criterion is optimized. The particular criterion we looked at was modularity. We are optimizing modularity with that particular algorithm. Other techniques, which we didn't see yet, do optimize density. So you can optimize some criterion, like for example density, or for example modularity. And there are others. Okay, all these, and I'm going to answer to your question, all these techniques, algorithms, take into consideration a network with its links and define density or modularity or any other criterion based on the link structure. That's different in vertex clustering, which we didn't see yet. I just skipped it in order to give you, as fast as possible, a first tool for community detection. So I skipped vertex clustering. We will see that later, in order to give you a first tool for community detection as fast as possible. So this one is based on the link structure, density or modularity. Vertex clustering, which we will see, I think, today in the afternoon, is based on the node information. Yeah, we analyze nodes or vertices. Yeah, vertex clustering. Vertex is synonym for edges. So the nodes or vertices are clustered based on their information. So for example, if we observe a network where the nodes are customers, we can do community detection based on clustering of customers. But then we don't take into consideration explicitly links. And that's the answer to your question. Vertex clustering takes into consideration just node information. Quality optimization takes into consideration basically link structure without considering node information. And that already gives us an idea. Of course, you can combine both. And
okay. Yeah,
so
thank you very much.
here you're using link information, and in clustering, you're using node information. Okay?
Okay, thank you.
Yeah, welcome. Yeah, vertex clustering. Clustering vertices based on their attributes, but not using links. Any other question so far?
Yes, regarding the example, we've had a undirected graph. Are there like big changes required to the formula or the algorithm to support directed graphs, or is it just ready to go as is?
Okay, we will step into the R code in a couple of minutes, and there we can see the parameters to define the direction, or we can define the type of graph. Let's see that later. Okay.
Okay.
Any other questions so far?
Yes, about the modularity. So, although we understand how to calculate the modularity now, would you mind explain the meaning behind the modularity? Like, what does that represent? What's the value represent? And how to interpret the value?
Okay, so apparently I didn't succeed in making clear this concept here. What we see here is a difference between two numbers. The first number is what we observe, number of edges in the community. On our whiteboard, in the example on our whiteboard, that was 6. We observe 6 links in our community. But we subtract from this number another number of links, and that's a bit more abstract. That's the expected number of links we would have in the community if the degree would be randomly distributed among all nodes. Let's see how that works on the whiteboard. So modularity for this community, how can we calculate modularity for this community here? We have to subtract two numbers. So one number is 6, which is the number of links we do observe here. Yeah, we're just counting 1, 2, 3, 4, 5, 6. Number of links within that community. Minus, and now we need a number that's not that easy to calculate. That's the expected number of links we would have inside this community if the degrees of all nodes inside that community would be evenly distributed over the entire network. So we have to look at the distribution. So this node here has 2 links. The degree is 2 here. This one has 2 as well. This one here has 2 as well. And so on. This one here has 3. The example, of course, doesn't tell everything. But yeah, even here in this example, we can see a difference. So the degree here is 3. Here it's 3 as well. So what I'm saying is the distribution of these numbers inside the community is different to the distribution over the entire network. If we would use the distribution over the entire network, then we would have less links inside the community. So we have inside the community, we do observe 6 links, and we have to subtract the number of expected links we would have if the distribution of the number of links would be homogeneous all over the network. In that case, we would have less links here. How many? Yeah, that's not easy to calculate right away. But the notion is what we observe minus what we would expect if it were evenly distributed.
So does that represent? So if the modularity is high, for example, it's approaches to 0. That means it's just like a normally distributed
community. Exactly.
But if it's a large negative number, it means the community is not pretty dense.
Yeah, it's less than average. The distribution is less than average. Let's take a simple, maybe a ridiculous example. Let's think of telco customers, and we have, no, not telco customers. Let's say visits, people visiting each other. Okay, so we have people that are living in large cities all over Germany. Okay, so we take all people living in Germany as our social network. Nodes are all people living in Germany, and we have and links are people that visit each other. Okay, so they visit each other going to the other one's house. And within large cities like Berlin, Cologne, Munich, there will be a high number, okay, because they are close to each other, supposedly. I don't know if it's correct. Maybe people are isolated. We know that people in big cities are isolated, but there's a different issue. So let's assume people in cities visit each other more often. I know that it's not always the case, but that's another story. So people inside large cities visit each other very often. So there we have many links. All over Germany, we have a distribution, but people on the countryside, they visit each other less than on average. And in that case, modularity would be negative. Did I explain myself? So we observe the entire social network, which has a distribution of all number of links, all number of visits. Inside large cities, these visits are more frequent. Those are communities. On average, we have a certain number of visits, but on the countryside, it's below the average. I think that makes it clear. So the expected number of edges in my example would be the average of all visits all over Germany. In large cities, it would be above the average. On the countryside, it would be maybe below the average. Did I make clear the idea?
Yes.
Any other comment on this? Anybody else did not understand the idea of this calculation? So again, edges inside the community is what we observe. minus the expected number of edges for a random distribution. Okay.
The screen is not showing the whiteboard, I suppose.
So I think here we go now. Again, edges inside, what we observe, inside Cologne, there are many visits, but all over Germany, there would be less. So that means in Cologne or in Aachen or wherever, we have more than average. That means there is a community. Okay.
I see. Thank you. So, in that case, in the recursive method in Lauven method, we would expect the modularity to be high, but isn't that means that we would expect a more intense community instead of a more loose community like the countries that I mentioned when we define a community?
I didn't get your point quite well. So in this example, for example, we put together nodes 1, 2, 4, 0, 5 into one community because the interaction among those is higher than on average in the entire network. Same here, nodes 8, 9, 10, 12, 14, 15, we put them together into the red community because interaction among them is higher than in the entire network.
I see. Thank you.
Okay, welcome.
I totally understand. Thank you.
Yeah. So what I would like to do before the break is to go to this web page we see here, and there we have R code in order to apply exactly this algorithm. So if we go to, that's exactly the web page. Let me see if I can share that screen. Here it is. Okay. You can see now my screen, which says community detection and visualization in R.
Yes.
Okay. So there is a web page where we first see this figure, but then you can find R code. It's a simple document, okay, where you find R code, which has been applied on this data set. The data set is about transactions where we have, for example, money transfer from an originator to a beneficiary. So from A to B, there is money transfer with this amount from Gera in Germany to Abu Aris in Saudi Arabia. The branch and so on. So details are not important here. So the author of this webpage offers R code. Okay, so we have pieces of R code here, and he also offers a social network. You don't have to build your own social network. You can use that social network. You can download the data, yeah, for this fake transaction data set. Okay, I think it's 126 nodes. Okay, here we have 126 nodes. And then there is R code, even with commands, move originator and beneficiary to the first and second columns with the respective R code. Then create a graph with the respective R code, and so on. And that's what I did. And that's what I have here in RStudio. Let me share this screen. So you can see now the screen with my R interface. RStudio? Yes or no?
Yes, we can see.
Yeah, so what you can see here is the first, sorry, the first line, that's just the web page. Then we are, what I did here is I just copied the R code from the web page to my studio. And if I go through this, I can read data. Of course, the only thing I had to do is to establish the path. So I have to read now from my path. I copied the data set, the fake data transactions I copied to my path. So you have to establish your own path. In my case, it's, sorry. So in my case, it can be found here in this path. That's what you have to establish to read the data set into what's called here my data. And from then on, you just apply. I just copied what can be found on the web page. You're still on my R page. So fastgreedy.community, that's the command which creates communities applying the algorithm. So it's just one line applying the community detection. And then the author provides visualization. What I do now is just running the entire piece of code, Control Enter, and now you can see here on the window, on the right lower part in the window, you can see the result of the R code. Okay, so that's what I wanted to show as fast as possible. That's what you asked for yesterday, if I could provide R code. So that's a first piece of code you could use. And of course, you could modify it and apply it to your own data set. So here you can see how to read, in that case, CSV files into R, my data, and from then on, you just apply the commands that are given on the web page and commented on the web page. By the way, yeah, there is a question. Vinodeep raised his hand, please. Vinodeep.
Professor, you mentioned about these two algorithms, right? Newman-Moore and Luvian method for community detection. And how do we apply it over here? Because when we see fastgreedy.community in the fastgreedy.community, so how do you know which algorithm? Maybe I'm asking a stupid question, I don't know. But how do we determine which algorithm is being used over here?
Okay. To be honest, for me, it's the same. Let me explain my answer. In our classes, I'm going to introduce some concepts. I'm going to introduce different algorithms, different techniques for you to know, let's say, conceptually speaking, to know the tools. That's one element. The other element is to do the consulting for your customer. And in that case, knowing the time restrictions, for me, it's exactly the same which software tool you use, which language, and which algorithm. Okay, so I don't want to put some restrictions on software tool or language or algorithm. The answer to your question, Vinodeep, is up to you. You can use any algorithm. What I want you to do is let's say, simulate a real world consulting project. That means convince your customer that you have a good understanding of the problem. Please explain me in your presentation that you did understand my problem. So I want you to convince me what are the nodes, what are the links, what is the application about. Then what are the communities you found? And again, I don't want you to use a certain algorithm or to use several algorithms. That's up to you. I want you to convince me that you know how to apply community detection whatsoever algorithm. There are different algorithms, but I don't care about that. In this particular case, in this, let's say, simulation of a real world project. And that's it. That's my answer to your question. You can pick the algorithm you feel more comfortable with. But of course, it's important to understand that that's only part of the story. In a real life consulting project, of course, you should apply different algorithms. You should provide the best solution you could obtain, and so on. But understanding the time limitation, we have just 5 days in total. I don't put any restrictions on the particular algorithm. I think I repeated 3 or 4 times the same answer, but I think it's important. Okay, Vinodeep?
Thanks, Professor.
Okay, any other question, comments so far? Okay, I think that's a good point where we can have our break, lunch break for you. For me, it's breakfast break. It's 8 now. Yeah, it's 1 p.m. for you. So let's have a break here. And then in the afternoon session, we will go into the other. Just let me go back to the PowerPoint presentation. Okay, so what we did so far is we saw one technique for quality optimization. Okay, so we introduced the notion of modularity. I also mentioned an algorithm, the Louvain algorithm. We saw an application to the telco network. All this within quality optimization, and at the end we saw R code, one particular application using R code for quality optimization. The particular quality criterion which is used there is modularity. There are other techniques which, instead of modularity, use, for example, density or any other measures, as can be found here. Okay, and from now on, you do already have one tool to do community detection. As Vinodeep said, it's not the only one, but I don't care if you use one or another technique. Whichever technique you want to use, that's fine for me in the project. Okay, so let's have our lunch break here. It's now almost 1 p.m. and we are back at 2 p.m. And then we have the afternoon session 2 to 6 p.m. Okay? Okay, see you.
See you.
Bye.